Hello and welcome to this look at the Gibbs equation delta G equals delta H minus T delta S. I'm going to focus on the effects of sign and magnitude of the enthalpy, the entropy and the temperature on delta G. So what's the significance of the signs of each part of the Gibbs equation? Well, for the reaction to be feasible or spontaneous, the delta G value must be below zero or negative. If the enthalpy change is very positive, e.g. an endothermic reaction, it's going to be harder for delta G to be mathematically negative as you're starting further from zero into the positive realm of the values of the integers. So if T is high, that makes the T delta S part, in other words this section, larger in magnitude. So the sign of delta S can decide if delta G is negative or not. So if delta S is positive, a minus and a plus go together to make a minus, which means this is more likely to be negative. If this is negative, then a negative delta S plus minus T delta S, two negatives together, make a plus. So that pushes it further into the positive side of the integer spectrum. In other words, further away from zero. So finally, the entropy change itself. A positive delta S value means subtracting T delta S from delta H is likely to lead to a negative delta G and vice versa. So let's look at the various combos. So let's explore each one in turn. If you've got a positive value for delta H to start with, a negative value for delta S combines mathematically with a minus sign in front of T delta S to add the size of T delta S to an already positive delta H value. So no matter what the temperature, delta G will always be positive, and therefore the reaction will not be spontaneous at any temperature. So in the second scenario, you've got a negative value to start with. So if you have a positive delta S value, that will combine mathematically with the minus sign in front of T delta S to subtract the size of this function, T delta S, from an already negative delta H value, meaning that at any temperature, delta G will always be negative, so the reaction will always be spontaneous. Moving to the next scenario. With that combination at low temperature first, you have a negative value to start with for delta H. A negative value of delta S combines mathematically with a minus sign in front of T delta S to add the size of T delta S to an already negative delta H. Now, if T is small, T delta S will be small enough in magnitude and it won't add up to beyond zero. So what will happen is delta G will still be negative, it will be spontaneous, but delta G will be not very negative. It'll be a little bit closer to zero. So therefore the reaction will be spontaneous at low temperatures. If we have the same scenario, but we now increase the size of T, what happens this time is T delta S will be large in magnitude enough now, and it will add up to a value greater than zero. Remember, you're adding T delta S as a positive value to a negative delta H. If T delta S is big enough, it'll push the answer to that mathematical function beyond zero, and therefore delta G in this scenario will be positive, and the reaction will cease to be spontaneous at higher temperatures. So let's look at the next scenario. Let's first of all consider low temperature. You've got a positive delta H value to start with. If delta S is positive, that will combine mathematically with a negative sign in front of T delta S to subtract the magnitude of T delta S from a positive delta H. Now, if T is small, T delta S will be small in magnitude, and the subtraction we've just talked about will not push delta G below zero. So at lower temperatures, this combination of delta H and delta S will be non-spontaneous. So therefore, this reaction will not be spontaneous at low temperatures because delta G will still be positive. If we raise the temperature this time, so still the same relationship between T delta S and delta H, but if T is larger, the subtraction will push delta G below zero. So this will now make delta G negative and the reaction will be spontaneous, but only at high temperatures. So let's have a look at how this might come across in some exam questions. We'll start with a multiple choice question. So it says the feasibility of a chemical reaction depends on the temperature and the signs of delta H and delta S. This means the combination chosen must end up with delta G being negative at high temperatures but positive at low temperatures, because it says which row has signs for delta H and delta S for a reaction that is feasible at high temperatures but is not feasible at low temperatures. So to start with, to make this work, you need a positive delta H value. So we can eliminate C and D because they start with a negative delta H value, making it more likely that delta G is negative in spite of the size of T. So next, let's have a look at A and B. If you have a negative delta S value, the minus sign in minus T delta S would add the size of T delta S to an already positive delta H value, making delta G positive at all temperatures. This eliminates answer B, because this would be unfeasible at all values of T. Therefore the answer must be A, because if T is large, then T delta S will be large enough to give a value below zero when subtracted from a positive delta H, but not if T is small. So therefore, it's not feasible at low temperatures, but it is feasible at high temperatures. So here's a different approach, a 2 marker. It says the enthalpy and entropy changes of a reaction both have a negative sign. So this means you start with a negative value for delta H, but are adding the magnitude of T delta S to this because it's minus T delta S with delta S being negative, so 2 minuses make a plus. So the larger T is, the more likely the value of delta G will actually end up being greater than 0. So at low temperatures, T delta S will be small enough in magnitude for delta H minus T delta S to still be a negative value, meaning the reaction is feasible because delta G is still negative despite being closer to 0. However, at high temperatures, T delta S will be larger in magnitude, so this time delta H minus T delta S will have a positive value. This means the reaction is not feasible because delta G is now positive. The mathematical answer to the delta H minus T delta S expression is now above 0. Okay, I hope this has been a useful look at a potentially tricky aspect of entropy where you're trying to compare positives with positives, positives with negatives, and negatives with negatives. But if you need to go back and play it one more time to get it clear in your head, please do so, obviously. So again, I hope it's been useful. Until next time, thanks for listening and see you soon.